Okay, Chapter 8 problems are all about rotational motion, so we'll start with a problem that just involves definitions. An airplane propeller is rotating at 1900 RPM, that means revolutions per minute. Compute the propeller's angular velocity in radians per second, and how many seconds does it take for the propeller to turn through 35 degrees. So for part A, they want us to take the omega that's given as 1900 revolutions per minute and turn it into radians per second. So that's just a conversion. So we want to go from revolutions to radians and from minutes to seconds. So we're going to set it up like this. One full revolution is 2 pi radians. 1 minute is 60 seconds. So we're going to take 1900, multiply by 2 pi, divide by 60, and we get 199 radians per second. So that's part A done. Part B, how many seconds does it take for the propeller to turn through 35 degrees? Now we need to use our definition of omega is delta theta over delta t. So we know omega, we know delta theta, 35 degrees, and we want delta t. So just rearrange it. Delta t is equal to delta theta over omega. And delta theta, remember, theta should always be in radians, so we're going to have to do a conversion of degrees to radians. Remember, 1 revolution is 2 pi radians, or 360 degrees. And if you put that into your calculator, you get 0.611 radians is 35 degrees. So delta t is 0.611 over 199. Which is 0.00307 seconds, or 3.07 milliseconds. Okay, so it's a pretty easy question. Typical kind of calculations. Often you'll have to convert revolutions per minute to radians per second and degrees to radians. So make sure you know how to do those kind of conversions. Okay, the next question. This involves the equations of motion at constant acceleration. So let's write those down, remind ourselves what they are. So we have the same 3 equations that we had for chapter 2 and chapter 3, except now we've replaced our letters with Greek letters for omega instead of V, alpha instead of A. And we put in theta instead of X. So those are the 3 equations. And now remember, we write down the things that we know and that we don't know in the equation. So we've got omega, omega 0, theta, theta 0, alpha, and t are our 6 unknowns. Alright, so we've got the rotating blade of a blender turns with a constant angular acceleration of 1.50 radians per second squared. So that's alpha, 1.50 radians per second squared. How much time does it take? So it's asking us what's t, to reach an angular velocity of 36.0 radians per second starting from rest. So that gives us omega 0 is 0 because it starts at rest, and omega final is 36.0 radians per second. And we don't know theta, we don't know theta 0. Okay, so we know omega, omega initial, and alpha, and we want t, so the obvious equation is to use that first equation. So omega equals omega initial plus alpha t. Rearrange it, that means that t is equal to omega minus omega initial over alpha. So put in our numbers. Final velocity is 36, initial 0, divide by the acceleration 1.50, and we get 24 seconds. So it takes 24.0 seconds. Got to get 3 sig figs for everything here. 24.0 seconds to speed up to that speed. Now I want to know how many revolutions does the blade turn in this time interval. So what is that? We want to know what's delta theta. And of course, remember, when we get our delta theta, our answer is going to be in radians. We'll have to turn that into revolutions. All right, so we want delta theta, and we've got, now we know our t, we know alpha, we know omega initial, omega final, and we want delta theta. So we can use either of these two equations. I'll use the second one. Okay, so delta theta is equal to, so I'll use the third equation, omega 0 t plus 1/2 alpha t squared. And the reason I use that equation rather than this middle one is just because I don't have to do any rearranging. The more algebra we do, the more chance that we're going to mess something up. Okay, so that's delta theta. Remember, delta theta is theta minus theta initial. So omega 0 is 0 times t plus 1/2 alpha, 1.50, times t squared, 24.0 squared. And I get 432 radians is my delta theta. Now that's not my final answer because I need to express that in revolutions. So delta theta is 432 radians. Now I want to do a conversion from radians to revolutions. One full revolution is 2 pi radians. And so I get 68.8 revolutions as my answer for part B. So we just do these problems exactly like we did the problems in chapter 2 for one-dimensional motion. Just now we're using the Greek letters in our equations instead of x, v, and a. Third equation, third problem involves torque. Okay, so we've got a mechanic using a wrench to loosen a nut. That should be loosen. The wrench is 25.0 centimeters long, and he exerts a 17.0 Newton force at the end of the handle at an angle of 37 degrees to the handle. Okay, so let's draw a picture of what we have. We've got, quickly draw, here's my wrench. I've got my nut inside the wrench. I'm told that the length here is 25.0 centimeters, and he exerts a 17 Newton force at the end of the handle at an angle of 37 degrees to the handle. So he puts on a force like this, where that angle is 37 degrees. What torque does he exert on the nut? Okay, so we know our equation, torque is equal to Rf sine theta. R is the distance from the force to where the axis is, so it's going to be 25 centimeters. F is the force that he applies, 17 newtons, and theta is the angle between R and F, which is 37 degrees. So it's just directly plugging in. Okay, so R, 25 centimeters, so I'm going to put that into meters, 0.25 meters. Force is 17.0 newtons. And the angle is 37 degrees. And I get 2.56, and the units for torque are Newton meters. Okay, so 2.56 Newton meters is my answer for that one. Okay, so now I've got my torque for part A. What's the maximum torque that he could exert? Well, remember, torque is Rf sine theta. So R and F are fixed, but I can vary my sine theta. And the maximum sine theta is 1. So the maximum torque is just equal to R times F when sine theta is 1. So that would be 0.25 times 17, which is 4 1/4 Newton meters. Okay. What orientation would the force have to be at? Well, we need to have it so the sine of theta is 1, and we know the sine of 90 degrees is equal to 1, so the torque should be maximum when the force is perpendicular to R. So if we draw a picture, here's our wrench again, the same orientation. We want to put our force perpendicular to the handle so that we have 90 degrees in there. Okay, so here's another torque problem. Now I want to calculate the net torque about the point O for the two forces applied as in the figure. Okay, the rod and both forces are in the plane of the page. So here I can see when I printed this, my picture got all messed up. I'll try and fix it for when I have it. But this is the point O. This force F2 should be applied at the 2 meter mark, and F1 is applied at the 3 meter mark. Okay, so I've got one force coming out at 2 meters, one at the very far end at 3 meters. Okay, so what's the net torque? So I'm going to have two torques, one torque from force 1 and one torque from from force 2, and I got to add those together to get my net torque. Okay, so torque 1 is R1 F1 sine theta 1. Okay, so R1 is the distance from the axle to where the force is applied. So that's going to be 2 meters plus 3 meters. So we got 5 meters. The size of the force is 8.00 newtons. And the angle between R, so here's my R vector, here's my F, that angle is 90 degrees. So we got 5 times 8, and I get 40 Newton meters. Okay, you see I left a space there. Why did I leave a space there? Because after we calculate the torque, we need to think about what direction it's in. So is this torque such that it's going to rotate the thing clockwise or counterclockwise? So if I imagine, so I'm going to put my pen down on the page, if I push down on my pen like this, rotate about the cap, you can see that the pen would rotate around clockwise. So force 1 is going to rotate the bar clockwise, and so that means it should be a negative torque. Okay, torque 2 is going to be R2 F2 sine theta 2. Alright, so R2 is the distance from O to where the force is applied, 2 meters. F2 is 12.0 newtons. And the angle is 30 degrees. So I've got 2 times 12 times sine of 30. So that should be 12 Newton meters. And again, leave a space for a sine. So now I've got, put my pen down in the same orientation. Now I'm pulling up on my pen like this. Pulling up on the pen would make it rotate counterclockwise, so that's a positive torque. So my total torque is torque 1 plus torque 2. So that's negative 40 plus 12, which is negative 28 Newton meters. And I should put 3 sig figs because I was given everything in 3 significant figures. So minus 28.0 Newton meters is my net torque. So that means that the rod rotates counterclockwise. Okay, so now let's bring in the concept of torque and moment of inertia now. So now we're going to use Newton's second law for rotation. Torque is equal to I times alpha, rather than, remember, we had force equals mass times acceleration for linear motion. Okay, so we've got a merry-go-round and a kid pushing a merry-go-round. We're told the moment of inertia for the merry-go-round is 2100 kilogram meters squared. The child applies an 18 Newton force tangentially to the edge of the merry-go-round for 15 seconds. So let's draw a picture. We've got, here's my merry-go-round. It's got a radius of 2.40 meters, and the child applies a force tangentially, so that means perpendicular to the outside. So that's at 18.0 newtons. So that means that that angle is 90 degrees there. Okay, and we want to know if it's initially at rest, what's its angular speed after this 15-second interval. Okay, so what happens here? Well, the child applies a torque, and that torque causes an alpha. So we need to calculate alpha is equal to the torque over the moment of inertia. Torque is equal to R times F times sine theta. R is the radius of the wheel. That's where the child applies the force at, so 2.40 meters. The force is 18.0 newtons, and the angle is 90 degrees. So the torque that the child applies is 43.2 Newton meters. So that means the angular acceleration is the torque, 43.2, divided by the moment of inertia, 2100. And so the angular acceleration is 0.02057 radians per second squared. Okay, so now I know alpha. I know what else? I know the child applies the force for 15.0 seconds, so that's time. It's initially at rest, so omega 0 is equal to 0, and we want to know what is omega after 15 seconds. Alright, so what equation do we use for that? Well, we know omega is equal to omega initial plus alpha t. I know alpha t and omega initial, so I just plug the things in. So omega 0 is 0 plus alpha 0.02057 times the time, and I get 0.3086 or 0.309 and 3 sig figs radians per second. And that's my answer for part A. Okay, so I had to do a little bit of work first to get my acceleration, and then once I had my acceleration, I had to use my kinematics equations to find the speed. Alright, part B now. So here's my answer for part A. Part B, how much work did the child do? Okay, well, how are we going to calculate the work? Work is going to be equal to the change in kinetic energy of the merry-go-round. So that's 1/2 I omega squared minus 1/2 I omega initial squared. The initial kinetic energy is 1/2 I omega squared, omega initial squared, and the final kinetic energy is 1/2 I omega squared. Okay, so work is equal to change in kinetic energy. That equation that we had from chapter 6 still works. Alright, so now we know I, we know our omegas, and in fact omega initial is 0, so that initial kinetic energy is just 0. So it's 1/2 times I, 2100, times omega squared. Omega is, I'm going to put in the unrounded number, remember, don't round till the very end, and I get 99.98 or 100 exactly, and the units for work, the units for energy are joules. Okay, so that's the work. And part C, what's the average power supplied? Well, power is work over time, so 100 joules, and it took them 15 seconds, so I get 6.67, and the units for power are watts. Okay, so this is using Newton's law for rotation to solve some energy problems. Okay, the last topic in the chapter involves conservation of angular momentum. So angular momentum, L, is equal to I times omega. And we know that if it's conserved, if there's no external forces, then I0 omega 0 equals I times omega. So a diver comes off a board with her arms straight up, her legs straight down, and she's got a moment of inertia of 18.0 kilogram meters squared in that location, in that orientation. Okay. She then tucks down to a ball, and her moment of inertia drops to 3.6 kilogram meters squared. And while she's tucked, she makes 2 complete revolutions in 1.0 seconds. So the question is, if she hadn't tucked, how many revolutions would she make in the 1.5 seconds it would take her to go from the board to the water? Okay, so what we want to do is we want I initial, omega initial is equal to I times omega. So I initial we'll consider as 18.0. I final is 3.6. Okay, omega initial, that's something we're going to have to figure out. Omega final is delta theta over delta t. And we're told that she makes 2 complete revolutions, so that's 2 times 2 pi in 1 second. So she's got 4 pi radians per second. Okay. So I've got I0 omega 0 equals I times omega. So omega 0 is equal to I omega over I0. So her moment of inertia when she's tucked is 3.6. her speed was 4 pi radians per second. Divide by what she had initially, so she had 18 kilogram meters squared, and we get 2.51 radians per second. Okay, so how many complete revolutions would she make in 1.5 seconds? Delta theta is equal to omega 0 times t, assuming that there's no angular acceleration. Okay, so we've got 2.51 times 1.5, which is 3.77 radians. How many revolutions is that? So to get revolutions from radians, one revolution is 2 pi radians, so I get 0.6 revolutions. Okay, so you can see that when she had the bigger moment of inertia, her omega was smaller than when she had the small moment of inertia, and thus she does fewer revolutions on her way down.